This is a recording for Edexcel Further Pure 1. Vectors 1, the vector product. Section 1.1, vector product of two vectors. Before you continue with this set of videos, you need to be familiar with the following ideas from your pure mathematics, your core pure. Firstly, the idea of a column vector A, B, C in 3 dimensions, and then being able to calculate the magnitude of that by the extended Pythagoras' theorem, a squared plus b squared plus c squared. The idea of unit vectors I, j and k, so in 3 dimensions we have vectors of length 1 along the x-axis I, along the y-axis j, and the z-axis k. These are all vectors of one unit. You should have met the dot product a dot b of two vectors and know that it has a definition of being equal to mod a, mod b, and then cosine of the angle between the vectors. Also, although this is here not essential, it is useful to be able to find the determinant of a 3x3 matrix. That we will cover as we go through this set of videos, but hopefully you know the idea of a determinant and preferably to be able to work out the determinant of a 3x3 matrix. Now, if you haven't covered these ideas, I suggest that you wait until you have before you proceed with this set of videos. So anyway, assuming that you have covered those, let's move on. We have many ways of combining two vectors as a product. We already know that the scalar product a dot b is given by mod a mod b cos theta. We're now going to look at something called the vector product, which has the symbol a cross b. So we talk about this as being the vector product or the cross product of two vectors a and b. Now this is only true for vectors which are in 3 dimensions. So a, for example, could be the vector 1, 2, 3, and b could be the vector -2, 0, 4. And then we could calculate the cross product, and we're going to look at how we do that. The vector product, first of all, is another vector. So note it's different from the scalar product. The scalar was only a thing which has length. A vector product is definitely a vector. It has length and direction. We can see here the diagram shows us that the vector product is equal to a vector n, which importantly is at right angles to both the vectors a and b. Now, an alternative form of this is to say that a cross b is equal to mod a, mod b, and then the sine of the angle between the vectors. So this angle here would be theta, and then we have the lengths of the vectors a and b multiplied by the sine of the angle theta. That gives us the magnitude of this vector, and so to give it a direction we want to include then a unit vector in this direction, which is normally given the symbol n hat, so that we have that a cross b is mod a mod b sine theta, and the direction vector n hat, and the hat means it is of length 1. Now, the fact that we've got sine theta in here means that if a cross b happens to be equal to 0 vector, and a and b are themselves not equal to 0, this means that sine theta must be equal to 0, and therefore a and b are parallel. So vector a and b must be parallel. Conversely, we can say that if A and B are parallel, then the cross product will be 0. And that becomes important a little bit later on. So let's recap that then. We have our two vectors A and B with the angle theta. Then A cross B is defined as mod A, mod B, or the length of A, the length of B, sine theta, and n hat gives us that direction. And notice that it's perpendicular to both A and B. So that this is important. A cross B equal to 0 if they're parallel, or if they're parallel, then we can say that the cross product is definitely equal to 0. And later on we'll see that in use when we look at I cross I. So where we've got the unit vectors I and I obviously parallel to itself, and therefore I cross I is equal to 0. J cross J will be equal to 0 vectors. We can determine the direction of the cross product by using what's called a corkscrew rule. So if you look at the diagram here, we have a corkscrew which we're turning from A to B. So if we turn from direction A to B, now a right-handed, the usual sort of corkscrew, if we do that, will travel in this direction. So the corkscrew rule gives us the direction of the cross product A cross B. Now because of this corkscrew rule, we can see immediately that A cross B must be in the opposite direction to, in other words negative then, of B cross A. Because if we turn the corkscrew from B to A, it would travel in the opposite direction. An alternative to the corkscrew rule is what's called the right hand rule. And here we are with the right hand, with the first finger is always used for vector A and the second finger for vector B. So it's important to get those right. Now if you're using the right hand rule, it can be quite difficult to get your hand in the orientation that you require. However, either of these rules will give you the correct direction for the cross product. I want to apply these rules now to those unit vectors that I was talking about a minute ago. We've already discussed the idea that I cross I, J cross J, and K cross K must be equal to a 0 vector because sine theta of sine 0 will be equal to 0. Because sine 90 degrees is equal to 1, then we have I cross J must be equal to a vector of length 1. And if we think about the corkscrew rule, moving from I to J means that the corkscrew would move in the direction of K. So because it's length 1, then I cross J must be equal to K. If we go in the other direction, from J to I, then the corkscrew would move downwards, and so we can see that J cross I is equal to negative K. Similarly for J cross K and K cross I. The corkscrew will tell you whether it's in the positive direction of the third unit vector or in the negative direction. Now that concludes this particular video. In the next one we'll be looking how we can use determinants to find the value of A cross B.